Hello, everybody. I would like to welcome you to the latest edition of the EDAM Astrophysical Colloquium at Graz University. It is my pleasure today to introduce our speaker, Dr. Savita Mathur, from the Instituto de Astrofísica de Canarias, the IC on Tenerife. Savita did her PhD in 2007 on the topic of gravity modes in the Sun. And between 2008 and 2009, she was a postdoctoral fellow in India. 2010, she changed to Boulder as a postdoctoral fellow at the AJO, and then became a research scientist at the Space Science Institute. Since 2017, she's a Ramón y Caja Fellow at the IC, where we worked together for about 2 years. Now, I would like to invite you to give your presentation. Savita, please.
Thank you. Okay, so hi everyone. Thanks, Paul, for the introduction, and thanks a lot also for the invitation to give this colloquium. I'm very excited to talk to you today about the work we've been doing on studying the surface radiation and magnetic activity of solar-like stars, and especially in the context of where does the Sun stand. So all this work has been done with a lot of collaborators, and you will see their names pop up all along this talk. I also wanted to give some warning because I will be focusing on work done using photometric data, especially with the Kepler data on solar-like stars, whereas there are many other works that have been done on this subject using ground-based observations. So with that, I'll take you to this journey about trying to understand where the Sun stands among all these solar-like stars. So this is just a brief outline of the talk, where I'm going to start with some context, and then we dive into how we are measuring surface stellar rotation, magnetic activity using photometric data, and the results that we are getting in particular with Kepler, and then how we can study magnetic activity cycles and end up with a summary and perspective. Okay, so let's start with the context. So let's start with the Sun. What do we know about the Sun? We know that there is a magnetic activity cycle that's going on with the Sun, that this magnetic activity is not completely random. There's this regularity that we can see when we look at this diagram, where we see the migration of the spots appearing at a given latitude and then going towards the equator. And that the cycle for the Sun has a length of 11 years or 22 years if we take into account the magnetic polarity reversal. In addition to that, there are other shorter quasi-periodic variability that was seen with period of between 1 and 2 years. We also know that the Sun has gone through a period of low activity with the Maunder minimum. And here what I wanted to point out with this diagram is that even though the Sun is our closest star, we still have no accurate prediction on what the future length or strength of the cycles will be. So that's why we need to study other stars. First of all, to put the Sun in a broader context. So you can see that the Sun is just one point in this HR diagram. It's one point at a given moment during its life. So it's also interesting to study the Sun in time and make this solar-stellar connection. And during this talk, I'm going to focus mostly on M dwarfs to F dwarfs, as well as a little bit on subgiants. So in order to study other stars, large surveys have been led during several decades, whether it is with spectroscopy, spectropolarimetry, and here you can see some examples of variability that was seen in a sample of Mount Wilson targets, solar-like stars, most of them. And you can see that there are different types of variability with regular cycles or not, flat variability, or a variability that's random without any regular pattern. So another thing that we can study from all these observations is to look at the cycle period when we measure a cycle, of course, the cycle period as a function of the rotation period of the stars. And you can see these two branches that come up, the what Bohm-Wittense called the inactive branch and the active branch. And you can see how the sun just falls in between these two branches. And that's where came up the question about, is the sun a peculiar star? However, if we kind of change the representation, instead of having the activity cycle period, we plot the ratio between the rotation period as a function of the cycle, divided by the cycle period as a function of the calcium HK activity. We still see these two different branches, and the sun, which is the symbol A, seems to be not so much of an outlier, and it gets closer to this inactive branch. This representation, the rotation period divided by the cycle period, is a quantity that could be interesting in terms of mean field dynamo, trying to understand like the alpha dynamo and the quenching that can be seen in the star. So as I told you, so we're looking at the magnetic activity, but when we look at magnetic activity, we're also looking at the rotation of the star. And one thing that I will mention, and I wanted to talk about this a little bit here, is getting relations between the rotation of the star and its age. So that's something that was done almost half a century ago by Skomanic, who studied two young clusters and the sun. So the clusters are represented here, and here you have the sun at 4.5 gigayears. And you have rotation measurements, average rotation measurements, calcium HK observations, lithium observation. And Skomanic derived this law where we can see that the rotation period decays as a function of the square root of the age of the star, which is also known as gyrochronology. And this can be explained through the magnetic braking that happens with the stellar winds. So, so even though the sun is our closest star, we still, well, we know that there is a solar dynamo that's responsible for the magnetic activity cycle of the sun, but we still don't know all the detailed mechanism, which can be seen by the fact that we can't predict solar cycles. In addition, we've seen that the sun could be a peculiar star, so what's happening there? And this is why we need larger data sets of stars where we can have precise measurement of rotation, magnetic activity, ages, and internal structure. And that's where Kepler comes into play with a couple of 100,000 stars that were followed almost continuously for 4 years. And so that's why we are using this gold mine to look for answers about rotation and magnetic activity of stars. So, so photometric data mean that we are getting light curves from stars, and we usually work in the Fourier space. So here you have the power spectrum density as a function of the frequency for a solar-like star observed by Kepler. And sorry, and so we can see different interesting features in this power spectrum. The first one at low frequency are these peaks, which correspond to the surface rotation of the star. Then you have this background, which is actually representing the convection of the star, and this continuous background. And then you have this region here with a little bump, where you can see the solar-like modes for this solar-like star. And then finally, you have the photon noise that depends on the magnitude of the star. So here I'm just going to give a small reminder about what's seismology, very brief basics about seismology. So the sun or star is like a resonant cavity where you have modes that are excited by the turbulence in the outer convective layers. And these modes are characterized by 3 quantum numbers: the degree L, which gives the number of nodal lines that you have on the surface of the star, the azimuthal order M, that gives the number of nodal lines that cross the equator, and then the radial order that gives the nodes along the radius of the star. And then you have different types of modes that propagate. You have acoustic modes, for which the restoring force is pressure, and these modes are equidistant in frequency. I'll come back to that later. So you can see some representation of the wavefront of these modes reflecting at the surface of the star. So you have the high degree that reflects many times, and the low degree that go a bit deeper inside the star. Then you have gravity modes, for which the restoring force is buoyancy, and which are evanescent in the convection zone, and so they propagate in the radiative zone, and they have the property of being equidistant in period. But they are very difficult to detect because they have very low amplitudes because of the evanescence in the convection zone. And finally, you have mixed modes that result from the coupling between the acoustic and gravity mode cavities. So by using information from this mode, we can directly probe the deeper layers of the sun and the star. So if we look at this again, the power spectrum density for the sun, now this time for the sun as a function of frequency, there is one quantity that we can easily measure when the signal-to-noise ratio is high enough. No? This is the frequency of maximum power, nu max, which is actually gives information about the surface gravity of the star. And then if we zoom into the modes, you can see that there is this pattern that's repeated with the L equals 3, 1, 2, 0, 3, 1, 2, 0. And from there we can measure this the frequency spacing. So this repetition of the mode, it's just like measuring the octave of a piano, if you like. And this quantity is proportional to the square root of the mean density of the star. So by combining, just having these two quantities and combining it with a good estimation of effective temperature, we can have first estimation of the radius and the mass of the star with quite reasonable uncertainty. So these relations have been tested both theoretically and observationally, though we know that they can still be improved, and many works are being done right now in that sense. And as I said, we need a lot of spectroscopic data in order to obtain this mass and radius and to have the effective temperature needed to compute these values. So this is when we are measuring these global seismic parameters, but in the cases where we have a high enough signal-to-noise ratio, we can do some stellar modeling, and where we are using the individual frequencies of the modes. So either we can use a big grid-based model or do some boutique modeling like it was done with the Astroseismic modeling portal. And by using these individual frequencies, it was shown in Liberton and Goupil in 2014 that we considerably improve the precision of the age of the star. So this is a diagram showing the ages of a given star with different cases where I'm including, first of all, only spectroscopic data, and then little by little adding global seismic parameters and then the individual frequencies. You can see how the error bars are getting lower and lower. So the modeling of stars has been done now for quite a large sample of stars, several hundred of stars. And by doing this, we can improve the precision on the mass, radius, and age of the star, but we can also get information on the structure of the star, in particular the base of the convection zone, which is an important ingredient in the magnetic activity of stars. However, you still need to remember that this is model dependent, and we know that models are not perfect. Many of them still don't include magnetic field, or the rotation is not completely well understood either. So this is something you need to keep in mind. So here I just wanted to show you what's the status right now about seismic detections, whether it is with Kepler K2, but also ground observation. So these are all the stars for which we have seismic detection. I think with Kepler and K2 we have around 570 stars. Though now we have been adding 150 more, still with Kepler and K2. So this is a very nice sample that we have, where we can get ages more precisely than classical isochrone fitting, which can be useful when we are looking at trichronology relationships, for instance. Okay, so now let's move into the core of this talk, which is measuring stellar surface rotation. So here you have a time series from the Virgo telescope, the Virgo instrument that's on board the SOHO satellite. So you have the brightness fluctuation as a function of time. And what happens is that when you have spots or active regions at the surface of the star, then you will see some modulation in the light curve that's directly related to the rotation of the star. So from this, we can apply different techniques to look for the rotation period. We can use the periodogram as the classical method, which is fast and easy to compute. The only caveat about this method is that many times we can also measure half of the real rotation period, which happens when we have active visual spots that are diametrically opposite in terms of longitude. So that's why we've been using two other techniques in our pipeline. The first one is the time frequency analysis using wavelets. So here you have a period as a function of time, and what we're doing here is we are measuring the correlation between a mother wavelet and the time series that we're sliding it along time, and we are also changing the period of the mother wavelets, which gives us this wavelet power spectrum. And all the regions in red, orange are regions where the correlation is high, whereas light blue, dark blue, purple are low correlation. And then we can project this wavelet power spectrum onto the period axis, which gives you this global wavelet power spectrum, which is quite similar to a power spectrum. But the idea with this is that we can see if there are any changes in the magnetic activity of the star, for instance, but also see if there was any instrumental problem during the observations. And finally, the autocorrelation function is another way of measuring the periodicity in the light curves. This has been used in a very large number of stars. And this technique has the advantage of recovering the real period also compared to the harmonic that we get many times. Finally, we are also using the composite spectrum, which is just a combination of the global wavelet power spectrum and the ACF, which allows us to increase the power where it's present in both analyses. So in order to validate our pipeline, which combines the wavelets and the ACF, we applied it to simulations, to 1,000 simulated sinusoids that were injected in real Kepler light curves. And so here you have the true rotation period on the x-axis and the rotation period determined by different pipelines on the y-axis. And our pipeline, the one from the CE, was the one that was deemed as the best method in terms of completeness and reliability. So we've been applying all these different techniques to the full sample of dwarfs and subgiants that were observed with Kepler. So this is a sample of 160,000 targets. We've been using almost 4 years of continuous long cadence data with a cadence of 30 minutes, where we are also using 3 different filters of 20, 55, and 80 days. And also we're using PDC map light curves. So our light curves from CADAX are usually different apertures compared to the PDC map in order to increase the signal from the stars. So first of all, we analyzed the K and M dwarfs to start with a relatively small sample of 25,000 stars. And we measured around 15,000 rotation periods for that sample. By comparing our results with the literature, with the catalog of Macmillan 2014, for the stars that were in common, we did have a very good agreement. Here you can see the histograms in terms of effective temperature of the stars and also magnitudes. And one thing that you can notice is that we're getting, in general, more targets compared to Macmillan, which are in black for the Macmillan sample. And we're also getting more fainter stars with measured rotation periods. So one thing that I didn't say is that for that first work that was led by Angela Santos, we actually Angela did a lot of visual checking to confirm the rotation period of these stars. So since we were going to analyze more than 100,000 more stars, we didn't want to do all these visual checks again. So we went towards this machine learning technique where we're using the random forest. So it's the Rooster algorithms. This is a work led by a PhD student at the CESAC, Sylvain Breton. So basically, by training the stars where we had rotation periods from the K and M dwarf first catalog that we had with Angela, we trained the algorithm with hundreds of input parameters in order to have a very good algorithm to have a very good accuracy in terms of rotation periods that we retrieve. So first of all, the global accuracy was around 92%, but you can see here the rotation period retrieved by the machine learning and the true rotation period from the Santos 2019 catalog. And you can see that we do have some outliers. This is still a very small number, but because many of them are on the one-to-one line, but they come out easily to the eye. So 92% of the stars agree within 10%, and we managed to have flags in order to say that we need to visually check some of the targets systematically. So, for instance, stars with rotation periods above 38 days, we always check them visually. We also look at stars where we have harmonics present in different techniques in order to see if we are getting half of the real rotation period, etc., etc. We also look at stars where we have short light curves, less than 3/4. So after visually checking stars that we flag as possibly wrong or stars that could have issues, we end up with a 97% accuracy, which is quite good. So we applied this to this rooster to the FJ dwarfs as well as subgiants. Of course, we increased the training set so that F and G stars are also included in the training because they behave a little bit different compared to the K and M. And we managed to have around 40,000 detections of reliable rotation periods for that sample. So here you can see the fraction of detection in terms of rotation periods for G-type stars, F-type stars, and subgiants. Interesting features that you can see here are the fact that F stars usually rotate faster, which is what we expect because they have a thinner convection zone, so they are less subject to the magnetic braking from the stellar winds. The subgiants have slower rotators, which is also what we expect from the evolutionary point of view of the stars. So here you can see the actual numbers of the detection fraction, and what I wanted to point out is that while for the K and M we had more than 60% of detection fraction, you can see how it decreases and drastically decreases, especially for the G and F, which are more complicated, let's say, to get reliable rotation periods. Of course, for the subgiants, I'm not talking about this because they are supposed to be less active, so they are also more complicated to have rotation periods because they don't have so many active regions on their surfaces. But yeah, for the F and G stars, we're close to 30% of detection fraction, which was also pointed out by Macquillan in 2014. So here is the full sample of 55,000 plus stars. So this means we have 62% more rotation periods compared to the previous catalog of Kepler targets with rotation periods. We divided here into dwarfs and subgiants. So here you have the rotation period as a function of effective temperature. Things that you can notice is this gap that was also seen in K2 and the Macquillan paper, which we still don't understand. Maybe it's due to two different population of star formations that happen in the history of that field, or maybe something happening during the evolution of the star where faculae and spots are canceling out and making the detection of rotation period more difficult. For the subgiants, as I pointed out, we're also getting these nice slow rotators which were not present in the Macquillan sample. And okay, and this is another way of seeing this representation, the comparison between our rotation catalog and the Macquillan one, in dashed line for the Macquillan and solid line for us. And this is the 95th% upper edge of the diagram I just showed before, and you can see that we are getting indeed more slower rotators compared to the Macquillan sample, and this is closer to what was expected by Van Seders et al. 2019, I think, in terms of what was expected from theory. So among that sample, we actually had around 500 stars that for which we had detected oscillation modes, so like oscillations. They are represented in this HR diagram where we modified the log-G. We used, instead of the log-G, the mean large frequency spacing. And we had reliable surface rotation rates for 300 of these stars. Again, you can see the different histograms here. Nothing different, much different compared to what I just showed you. But for these stars, because they're seismology, we can have seismic ages. And so by focusing on stars where we had individual modes and where we could do the specific, more precise modeling, we noticed some interesting feature. So I'm going to focus here on this panel here. So you have the rotation period as a function of the seismic age of the stars, for effective temperature between 5,600 and 5,900 Kelvin. And in the black line here represent the magnetic braking prescriptions that we have used and that were scaled on the sun. So it's like this Comaneci law, but a bit more improved. And one thing that you notice is that many of our of stars older than the sun are actually below what we were expecting. So they're rotating faster than than what we would expect from the Skumanich law. One way of explaining this is to use a critical Rossby number from which the magnetic braking stops. We still don't know what would make this stop, but at least this seems to represent pretty better what we are observing. So this means that by using the classical gyrochronology relationships, we are only getting lower limits on the edges, or we can say that we can only apply gyrochronology on certain stars. The other thing you can see here is that for the sun, it seems to be just at the edge from where it should start to stop braking. So there was the question about whether the sun might be in this transition phase. So now I'm going to talk a little bit more about magnetic activity. As I said, when we are measuring rotation, we actually need the star to be active. We need spots or active regions in order to see the modulation in the light curve. And this modulation is dependent on how many active regions you have on the surface of the star. So we can define a photometric activity index, which is basically the standard deviation of the full time series. And so we call it the SPH, like the S index from spectroscopy, but the photometric X index. Another way of computing this SPH is to take into account the rotation period of the star. So we know that the rotation that we are measuring is due to the fact that there are active regions on the surface. So we can use subseries of length and integral time the rotation period. Here we are using 5. So that we are sure that the variability that we are measuring is related to the magnetic activity of the star. And then we can have this SPH as a function of time, and we can see that this star has actually some cycles going on, well, at least one cycle going on. So we validated this SPH measurement by using Virgo data for the sun, where we have other proxies of magnetic activity. So in blue here, you have the SPH, which is in all the panels as a function of time. And in red, you have the sunspot number, the calcium HK, the radio flux at 10.7, the mean magnetic field, and frequency shifts. So I'll come back to the frequency shifts later. But we can see that there is a very nice correlation between our SPH and these solar indexes of magnetic activity. So we can say that we can use the SPH to measure magnetic activity of other stars. So if we come back to the seismic sample, the stars where we had seismology and measured rotation periods, here you have the SPH as a function of rotation period, again for the 3 different categories of stars, F stars, G stars, and subgiants. And in dashed line here, you have the range of the SPH for the sun between minimum and maximum activity. And you can see that most of the stars are actually in a similar range of SPH. So they are compatible with the magnetic activity of the sun. If we go into a narrower criteria on selecting these solar-like stars to be solar analogs based on mass, effective temperature, log G, we have this sample of 18 seismic solar analogs. And you can see here the SPH as a function of age, the age again coming from seismology, and you can see how the SPH of these solar analogs are usually in the same range as the ones for the sun, except for these 2 young stars, but we expect that the younger stars would be more active. One thing that I wanted to point out here still about the SPH is that it's actually a lower limit of the real activity of the star because it depends on the inclination angle. So because if the star is more pull-on than at 90 degree, then we will see less the spots than if it were 90 degree. And also, like the S index or the calcium HK observation we do, it depends on the moment when we do the observations during the cycle for that star. So there are many other works that have been done in terms of solar analogs, solar twins. I'm not gonna go into much details about them, but this is the work done by Nascimento in 2020, where they selected 125 solar analogs based on their masses. And they found, so here you have again the SPH as a function of rotation period, and they find a few slow rotators in terms of solar analogs. So they are rare, but they can still be found. And then for the high SPH values, usually these are younger stars. Another work that, well, two works that were led by Reinhold in 2020 and 2021 with collaborators was the study of sun-like stars. So by selecting stars in the Kepler field that were close in terms of temperature, effective temperature and rotation periods to the sun, they looked at the R-var, which is kind of similar to the SPH with some caveats, but I will not go into this. And you can see the distribution for all these stars in terms of their R-var. Then they studied how the sun would be by mimicking different magnitudes in the same range as the magnitude of the Kepler targets. So they call this the noisy sun, and you can see where the R-var peaks. So we can see that actually the noisy sun has a lower activity compared to what we see for the rest of the sample, suggesting that maybe the sun is indeed less active than sun-like stars. However, one of the things that they did later is also model G-type stars and the light curves of G-type stars. And they found that actually, in many cases, solar-like stars with a solar-like rotation periods are generally undetected. So we don't measure rotation periods we wouldn't be able to measure rotation periods for the sun if it were observed like other stars. And so the sun would belong to this non-periodic sample, which is the sample where we don't have rotation periods. So here I just wanted to show what we can start to do also with the huge sample of stars that we have. So here you have the SPH as a function of the Rossby number. So the Rossby number is a very key parameter in when we're studying dynamo of stars. So here, by taking our sample of stars where we removed subgiants and by computing the Rossby number based on B minus V measurements to compute the Rossby using the noise formula of 1984, we have this very interesting diagram, which was also studied by Reinhold in 2019 and collaborators this year. So you can see this dispersion, which is something that we expect because, as I said, SPH is a lower value of the real magnetic activity of the star because of the inclination angle and when we are observing the star during its cycle. So we expect this dispersion, but we can see that there is this very interesting sharp edge here, which means that probably we are observing these stars with an inclination angle of 90 degrees and they are at the maximum of their activity cycle. And then here you can see the sun between the minimum and maximum activity. And so it's in this region where we actually don't have so many stars. So it goes in the direction that the sun is less active than the rest of the stars observed by Kepler, for which we detected rotation periods. So the last part of my talk is about magnetic activity cycles. While I showed you before that we can see the magnetic activity cycle of the sun by studying the spots and the migration, we can also use seismology to study magnetic activity. Indeed, we know for the sun that, so here in red you have the sunspot number as a function of time. The frequency of the modes vary as a function of the magnetic activity. So it's the frequency shifts are correlated with the sunspot number, whereas the amplitudes of the modes are anti-correlated with the sunspot number here. And this was then the starting point of studying the same thing on other stars. So HD 4933 was the first star where we did similar analysis. It's a star observed by CoRoT. It's more massive than the Sun. So here you have the flux as a function of time, the SPH, the amplitude of the modes, and the frequency shifts. And you can see this very nice anti-correlation between the amplitudes and the frequency shifts, suggesting that there is a cycle going on in the star. So that's one of the interesting things that you can do, but it's also pointing out the fact that magnetic activity suppresses the modes. And this is something that was also studied during the early days of the Kepler mission by Chaplin and collaborators in 2011, where we compared the level of magnetic activity of stars with modes detected in black and the ones without detection of solar-like oscillations. And in general, we see that stars that are more active usually don't show detectable modes. Later on, we did further analysis of a smaller subsample where we had removed some contaminants, but also taking only into account stars where we were indeed expecting to detect the modes due to their amplitudes compared to the noise level that we had. And we find the similar trend where the stars with seismology, where we detect modes in red, are in the same range as in the Sun, between the two dashed lines. Whereas for larger activity, we don't detect the modes. But we still have quite a lot of stars below in the same range as the Sun, for which we didn't detect the oscillations. So this is something different, another puzzle, but I will not go into details about this. So as I said, we can use seismology to look for magnetic activity cycles. And so this is a very interesting case of solar analog, more or less. Let me call the star Doris. So it was observed by Kepler, and it's a one solar mass, 4.5 gigayear, 21-day rotation period. But this star was studied, was observed for several decades in Cassium HK. And so here you can see that it has a very nice cycle of 7.4 years. Then you have the flux, the light curve obtained with Kepler, the frequency shifts for different degrees of modes, the amplitudes of the modes, and the SPH. And on the right, you have the same parameters, variables for the Sun, and just to you should notice that the scale are the same for both stars. You can see that the chromospheric activity for Doris is much larger than for the Sun. And one thing that I didn't tell you is that this star is actually metal rich. It has a 0.3 dex metallicity, and this can explain why we're seeing a stronger chromospheric emission and shorter cycle period. Having a more metallic star will increase the depth, will increase the opacity and then the depth of the convective zone, and making the convection more, it will make it stronger, and hence making the magnetic activity stronger for this star. So it's a nice way of, by combining seismology and magnetic activity measurement, we can have more input about what's going on in the mechanism of the dynamo for these stars. So I'm going to go very quickly about this. So I just wanted to point out that there are more stars for which we detected frequency shifts using Kepler. And then we can start to compare them with different stellar properties like ages, metallicity. There are also work going on that were done by Thomas and collaborators to study active latitudes by having constraint where they studied ratios of frequency shifts. So we are getting more and more information from seismology. So, okay, so this is almost the end of my talk. I started this talk by asking, where does the sun stand among all of these solar-like stars? And you would tell me, okay, you've been telling us so many things that maybe you're at loss. I would be at loss. So first of all, we were talking about the sun being peculiar in between these two branches, and then maybe by looking at the rotation, the sun might be in this transition. Then looking at solar analogs, it might have similar magnetic activity than other stars, but then it might be less active than other stars. So what's going on? So I'm not claiming that I will give any answer to this. This is not really the point. We still have, I think we have all these different pieces of the puzzle that we're trying to put together, but we might have still a few answers. So I will start here with the fact that we're saying that the sun is peculiar, but maybe also in a transition. And this is a work done by Travis Metcalf and Jen Van Seders, where they are suggesting that actually stars can be going from one branch to the other branch. And that's maybe what's happening with the sun being in transition, going from the inactive branch to the active branch. So that could make a nice coherence between what we're observing. Then in terms of the sun being less active than other stars or similar, with a similar activity, we have to remember that when we look at the seismic sample, so I was showing you the solar analogs that were seismically, where we had seismic detections. So these might actually be closer to the sun because we actually do have seismology. And in order to do the seismic detections, we need the star not to be too active. So it makes sense that they have similar activity levels than the sun. Whereas when you look at a broader range of solar-like stars, they might be more active than the sun. And remember that actually for the sun, we wouldn't be able to measure the rotation periods by using Kepler-like observation. So in terms of this sun in transition, we are trying to test that theory by doing long-term magnetic activity observations by picking stars that we think are before, near, or after this supposedly transition. And so we've been doing this with Travis Metcalf, Paul Beck, Jen Van Seders by using Las Cumbres Observatory. So we have this key project that will run until 2023, and we hope to have more answers about this in the future and see if some of the targets that we thought were going through this transition or not, before or after, indeed show or not magnetic activity changes. So this leads me to the conclusion of this talk. So we've seen that we are able to measure surface radiation and magnetic proxies for more than 55,000 dwarfs and subgiants observed by Kepler, which will help us understand angular momentum transport and hence have an impact on determination of ages. There are other works that are being done about clusters and binaries that I didn't talk about, but I just wanted to mention that these are also very important works going on in this field. In addition, we saw that there is an impact of magnetic activity on seismic detection. While we have some bias when we do seismic detection towards lower magnetic activity targets, we can still study magnetic activity cycles with seismology and having information on the stellar structure, and then study the detailed mechanisms of the stellar dynamo. And of course, we have TESS, Plato, and the LSST, which hopefully will bring more information and pieces to this puzzle. So I think I will leave you with that and take questions. Thank you.
Thank you, Savita, for a very nice talk, very comprehensive talk. You see the clapping hands in the lower corner. And I already see Aike has a question. Before Ike gets the word, I just want to encourage everybody to participate in the discussion, in particular the students. That's the reaction, thank you. But Ike was first, so Ike, please go on.
So thank you very much for the very interesting talk. You mentioned the faculae, but I assume when you have monochromatic light curves like from Kepler, you can always fit the light curve with basically just spots, right? You never need faculae to fit the light curve. So basically, it's very, very nice data, but we never know anything about the faculae. Is that correct?
Yeah, so we are not, at least in our work, we're not claiming we are measuring anything about faculae because it's such, I mean, it's all over the place, right? So it's integrated. And so, let's say that if we're having more of these bright points happening at the surface of a star, and we are integrating them and we have less spots, then we will still see some changes in the brightness, right? So I think it's a matter of combination of all these two features. But it's more complicated to measure faculae than spots, yes, or active regions.
Thanks.
And I think Florian is just going to continue in that line. Please.
Hello. Also, thank you for the very nice talk. Well, actually, I have one question more at the beginning for the rotation periods for the K and M stars. You showed a plot there. Maybe I was not listening carefully enough.
Oops, I think I went too fast.
Yeah, a little bit.
This one?
Exactly. Here we see in the rotation period and the effective temperature plots that we have at 2 points a lower value. What is happening there?
Oh, yes. Okay, so this one, this is not real. So this is just because, so when we're using the effective temperature, we're using a previous catalog of the stellar parameters of Kepler. And this is just because we were using two different scales of effective to measure effective temperature. So it's just a problem of scaling. So thanks for pointing this out. We should do this new plot by taking the new effective temperature scale. And then this one, I think this should be part of the bimodality that I was pointing out here.
Oh yeah, the gap here.
The gap that we have.
Okay.
I think that could be one of the explanation.
Okay, thank you. And also a second question. At the end, you said for a star like the Sun, using Kepler, we would not be able to detect these.
The rotation period.
Yeah. Is this true? Or when a star is somewhere outside with this activity that we have, that we wouldn't detect anything?
Well, it depends when we are observing the Sun, for sure, like low activity or high activity. But what's happening is that for the Sun, I don't have the plot, but because we have so many active latitudes, and it's when we're doing the wavelet analysis, it's kind of a mess. So it's not like the nice rotation. Like here, you can clearly see there's one nice rotation period, but we have features all over the place, and because of the when we are adding noise, the fact that we're adding noise to mimic the different magnitude of the star, then it's much harder to have a reliable rotation period. And many times we actually get half of the real rotation period because we have spots all over the place, and so that's what happens.
Okay, I see. Yeah, thank you.
Welcome.
Yeah, thank you. Next one, Andreas, please. Andreas, you raise your hand. You have a question?
I forgot to unmute myself. There we go. Yes, thank you for the talk. Very nice. I have one more general question. So, if I understood it correctly, is that the less magnetically active stars are easier to detect than the more active ones? Or because I think it was switched at some point.
Sorry, well, can you repeat?
The magnetically less active stars are easier to detect? Like on the last slide?
The magnetically active, less active stars. It depends. What do you mean by less active?
For the seismic measurements. Anyway, that's not the main question.
Okay.
The main question is actually, this plot is okay. So you said that the sun is in an atypical spot for this SPH measure. So this is now a scatter plot. Have you already tried like computing the probabilities of detecting certain types of stars, then correcting the bias for that? Because I assume this plot is now probably uncorrected.
Yeah, this is just what we are measuring. So there's not, no, we didn't compute any probability or anything, but yeah, that would be an interesting thing to add. This is just, yeah.
Because if you're able to quantify the bias somehow, you should be able to correct for that to a certain extent, and then maybe the star is typical again. But yeah, it's
a good point. Thanks.
Okay, that's
okay. Thank you. I continue with Desmond. In case you don't have a microphone, you can also put your question into the chat. And of course, I also invite more senior people to ask questions. It's not only constrained to students. Desmond, please.
Hello, good afternoon. Thank you very much for the very interesting talk. I had really some insights today. My question is regarding to differential rotation, because we talked a lot, or you talked a lot about the rotation period, and this is usually assumed as the rotation period on the equator, is my assumption basically. What do we have any insights? I think you mentioned it at the beginning. Do we have any insights on differential rotation from the data that was analyzed?
Okay, so I guess you're talking about surface latitudinal differential rotation, right?
Yes.
Yes, this is a very good point. I think, well, many people have been trying to measure differential rotation. I have to say it's very hard. It's very hard, right?
Yes.
Because we are not resolving, we are integrating the light of the star, so we don't know exactly what we are looking at. We don't know the inclination angle of the star either. We assume it's equator, but probably it's not. I mean, I think in average it should be higher latitude because of the average inclination angle of the star should be around 45 degrees. So that's what we are measuring. So yeah, but there were different techniques that were one of them, for the differential rotation, one of the technique that was pointed out by Reinhold and also Angela Santos looked at this was to look at peak height ratio. So normally you have the rotation period and then you can see the harmonics, right? Mm-hmm. And depending on at which latitude and how long you can see the active regions, the ratio between the fundamental period and the harmonic will change, and one will be bigger than the other one.
Okay.
This is something that we can try to use, but still we would need information about the inclination angle of the star, which we don't have. And this was also based on having only a few spots, which is not usually the case. So I would say that for the moment it's hard. It's still hard to have information on differential rotation. One thing that we also say is that when we have the error bars, the uncertainties on the rotation period, that might include part of the differential rotation. But that's as far as I would go for the moment.
Okay, thank you very much.
On the surface rotation, you mentioned that you're using machine learning.
Yes.
Is it only used to distinguish the systematic from the intrinsic signal, or is it also to estimate shape, migration, some features? What is the machine learning doing? And
no. Okay, so yeah, I didn't go into details, but the inputs of the machine learning are usually the same as they're coming from the rotation analysis. So we have the fundamental peaks from wavelets, the autocorrelation function, but also additional peaks that we might see in the power spectrum, the heights of the peaks, and we're also using Flipper and stellar parameters. So there are like 130 input parameters, and this is used first to select stars where we think there are rotation periods, to remove contaminants and things like this. And then once we have this sample of stars where we think there is a rotation period, we select from which technique and filter we want to take, we think the real rotation period is. So it's a two-step process, and it's just to figure out which rotation period we should use, because we have 9 rotation periods from different filters, techniques, and that's how we use this.
okay.
Because I think Axel was trying to annotate something.
Yes, I was asking you regarding this plot here.
Yes.
And how much of the change in SPH is actually due to a change of tau, the turnover time, versus the rotation period? Because in certain cases, it could actually be that much of the variation is due to tau itself and not because of rotation. Do you know anything about that in this case?
I don't have the plot. So we have the plot SPH rotation period. Sorry, I didn't put it, but part of this is coming from, sorry, I can't show you, but part of what we're saying is due to the rotation period. Part of this is coming from tau as well. So
do they have potentially opposite trends, these two? Because we have found similar opposite trends a little bit in the M67 data, and therefore I'm somewhat concerned and interested whether you might actually see similar
well, we did
here.
have, okay, sorry, no, I don't know why I lost my, oops. I lost my pointer. Well, but when we do the SPH, just SPH PROT plot, rotation period plot, we do have some kind of 2 things that are like this, and then by computing the Rossby number, it's kind of flattens a little bit and moves, like having this shape that you're seeing.
Okay, yeah, I see. Interesting, thank you.
On the noise 984 Rossby number, it should be noted that this is based on some crude scaling relations on the color index B minus V.
Yeah,
so there might be also some noise. Because
yes. This is just a basic computation of Rossby number that I've used. I did use at some point the latest paper by Lehtinen, who was also providing another scaling of the Rossby number. The shape more or less stays the same, but yeah, there are different features that appear, but I didn't show this here.
Where would you, the Rossby number needs to be calculated for a certain zone. Which would be the important one? The bottom or the top of the convective envelope?
Usually we take it in the full, in the full convective envelope.
So the average?
Yes.
Okay.
So what I had done in 2014 for the F-stars, we were computing the integral of the velocity, the convective velocity over the full convective envelope.
Okay. Should we proceed with the next question?
In the meantime, I don't know. So since I accepted something, now I don't see my...
I think you have the cursor to, well, some annotation. I see a cursor, some pen driving around.
I don't see it, so I don't know how to remove this.
Okay. Well, Lucas is the next one in my list. Could you please ask a question?
Yes. First of all, thanks for the nice talk. The first question was something similar like Paul asked about the machine learning thing. And because I'm interested in machine learning myself, I wanted to ask you if you know which training data you used, because you can't really use real data for it. You have to synthesize it, right?
No. So for the training, what we did was to use the K and M stars. So we had, does that work? I don't know if that's working. So we used the stars where we had measured rotation periods with Kepler. Can I go back up? Okay, so we used the sample of K and M stars as a training. So we're putting like all the information of the 9 rotation periods we're measuring from the 3 different filters, the 3 different techniques, as well as other inputs. So we are not simulating anything, and we just know from all the visual checks that were done in the previous catalog what are the real rotation periods. And so the machine learning is using all these inputs and knows what's the real rotation periods to get this training. I don't know if that's answering your question.
So basically, you're using already measured data.
Yes, that's for the
Okay.
that's for the K and M, and then we also added some FNG stars to have like to sample a broader range of targets, and then we applied it to the rest of the samples that we had.
Okay, thank you.
But then we also used some simulations, like the 1,000 simulations I told you about before. But I mean, it's kind of the similar way we are training the machine learning and then just apply it.
Okay, thanks.
The next question is by Diego.
Yeah, can you hear me?
Yep. Where are you calling in from?
Okay, great. I'm calling from Ohio.
Oh, nice.
Yeah, thank you so much for the great talk. Savita, could you please go back to the SPH versus Rossby number figure? So you kind of already talked about a little bit about the x-axis on this figure. I guess my question is on the y-axis. So it looks, I keep in mind this figure of, I guess, fractional X-ray luminosity to bolometric luminosity as a function of Rossby number. So this, which is another activity indicator.
Yeah.
So it looks kind of like that figure, but
yes,
not really.
We kind of have a saturation. That's right. What we see in the X-ray, right?
Right. So I guess my question is, do you have any insight on why? Is there something intrinsic with the activity indicator itself, or why it doesn't look as similar or as, exactly the same way as the X-ray one?
Well, I think the X-ray one, well, I have in mind the one by Wright. Is it Wright?
Yep.
I think they are not going so high, first of all, in Rossby, or if I remember, or I mean, the range of Rossby is not the same, right? And so I think we are probing a much larger range here than what they were doing. And then the fact that where the saturation is happening, I think it's because we are not seeing the same thing. The X-ray might be happening more it's in the corona or whatever of the star, whereas this is really photospheric, like closer to the surface. So we could expect that things are taking time to happen, and we don't see the same the saturation at the same place when we are looking at different region of the star.
Okay. Thank you.
Okay. Next one is Alexei Sharov, please.
Yes, thank you. One question from a PhD student studying solar granulation and its variability. And my question is about surface gravity. When you are speaking about surface gravity, when you tell, do you refer to the lower limit or upper limit? I mean, what is the standard in your understanding, the equatorial value or the polar value?
For the gravity, I would say it's,
for the surface gravity.
for me, it would be an average value rather than not
Okay,
really surface.
Okay, and they differ. Not much. Okay, I agree. The second question is about your earlier publication. You have written, I liked it, I was fascinated with your statement very much, that the horizontal extent of granular cells primarily scales with gravity. Do you still agree with this statement?
Yes, for the moment, yeah, we don't have any proof of not.
And I'm very glad to hear you and to see you. I'm fascinated with your presentations and publications. Thank you.
Thank you very much.
Yeah, so I hand over to Manuela. Oh, and yeah, okay, Manuela and then Timuri.
Okay. Yeah, repeating, Savita, thanks for this nice talk. It reminded me a bit on my PhD thesis. So I did also periodograms and wavelet analysis on sunspots. So it is possible to do wavelets. And we found distinct north-south asymmetry in all of the results. So my question would be, do you think that because you have different inclinations, as you already mentioned, that you see preferably northern hemisphere and southern hemisphere of the different stars? And we know that the two hemispheres, at least from the sun, they behave differently in rotation rates, in activity. So do you think that that could bias your results also in putting kind of two branches of results because you have preferably northern or southern hemisphere? Or do you think that most of the stars are observed in the ecliptic plane, so you see an average of these rotation?
No, so I think given some statistics work that were done, I don't remember who was that, but we expect to have more or less like a between 30 and 50 degree inclination angle for most of the in average. So yeah, that could be something. Actually, it's a very good point because I never thought about this. That maybe in some cases we just.
I mean, if you're interested, I sent you one of my old papers.
Yes, definitely you can. Yes, yeah. So that could also explain why in some cases we see less good
bifurcation.
Yeah. Thanks a lot. Yeah.
Okay. Good. Thanks.
Timuri, please.
First of all, thank you very much for the nice talk, Savita. And now I returning back to the facula. So we know that the total solar irradiance is composed by the increase by facula brightening and decrease by sunspots. Yeah? So if you look to the total solar irradiance, then it reaches maximum at the maximum solar activity. This means that the sun is facula dominating. This is known, right? So now, if you look to the influence of facula and the sunspots, we know that the sunspots have maximum when they are at the disk center, while the facula have maximum influence when they are near the limb. So maybe the combination of these two gives you the cancellation of to determine the rotation period in sun-like stars, in slowly rotating stars. What do you think about this?
So yeah, I think that could be one possibility, and I think that's something that Reinhold mentioned maybe. Yeah. I don't know. One of the first things I would like to do would be like to make real like simulations of what we would see, because many times when you do simulation, we usually leave out the faculty and we just have the spots and distribution and things like this. So yes, I don't know. I mean, that's an open question. That could be an explanation why we're not detecting rotation for stars more like the sun. I don't have much more to say about this, but yeah, it would be something interesting to study further.
Okay, well, I see we're already discussing possible new science here. You're always welcome to come here to Graz when it's allowed again. So
I would love to.
we'll work on that. And of course, some of us keep traveling down to Tenerife every now and then. So, are there any more questions? The floor is still open. I have to say I'm very happy with all the student questions. That was very well done. Very good questions.
Very good questions. Yes, thanks. That's good.
Before I close the discussion session, I just have a final question. Well, you showed, if you go to Strumanich, we were talking about rotation and activity, but there's a third one, and
it's the lithium.
We missed out on the lithium, which
I know you've been working on.
I love it. I love it. It's so complicated. But any word on the solar value of lithium, on the depletion?
Yeah, sorry, I haven't been working on this, so I wouldn't be able to answer this.
Okay,
I think you are better in a better place to do this.
Well, it's complicated. It's really complicated.
That would be my answer. Yes.
Yeah, that's also mine. Thank you, Savita, again for a very nice talk, very comprehensive talk, which was accessible to the students and the experts. This is what we're aiming for here in the Graz seminar. You see the reactions. And we continue. Now, normally we try to alternate stellar and solar. This time for some agenda clashes, we had 2 stellar talks. The next one will be kind of solar talk, and I yield to Manuela for the announcement.
Yeah, thanks, Paul. So the next talk will be given by Ximena Abrivaya. She will give a talk on astrobiology. The title is When Astrophysics Meets Biology, so re-estimating the UV habitability and stellar superflare impact on life through experiments. So that will be May 26, 5 p.m. We are all looking forward to that very interesting talk. And I hope you're joining us again.
Thank you, Manuela. I want to mention that all the talks that I announced are also listed in the TESS webpage and sent out via the internal email newsletters. If you don't have any access to one of those sources and you want to receive the invitations, please drop me a message and I will put you on an informal list to provide you with the information. The day is May 26th, as Manuela Eichis just put in the chat. This talk, as well as numerous of the other ones, including some from last year, are recorded and they are available for rewatch in my YouTube channel, which I just posted the link. Also, the link to the respective session is linked in the TESS webpage and will be distributed via the newsletter on Monday. Having that said, thanks everybody for coming. It's beautiful to see the big crowd and many collaborators and many no-names to join in the seminar. I hope you keep up the tradition and say goodbye from Graz and see you in 3 weeks. Bye.
Thanks, Paul. Bye-bye, everybody.
Okay,
Goodbye.
Bye-bye. Bye.
Bye.